My name's Kevin Bates. I'm the president of Sharp Development Company. So the catalyst of this project was really to see if we could demonstrate that renovating buildings to net zero energy with a very, very strong emphasis on the health and wellness of the occupants could be done in a manner that is more cost effective and more profitable for the ownership than renovating to meet minimum code. We believe that that's the only way it's going to ever resonate in the private sector and actually get traction and motivate people to renovate and develop in this manner. There's a lot of carbon involved in the embedded energy to create a concrete tilt-up building. About 30% of the carbon footprint of a building throughout its life is the production of that building itself. And a lot of these buildings were being demolished and hauled into the landfill. And so for us, having an impact on the carbon footprint going forward by energy reduction was important, but also recycling and repurposing the existing building mattered as well. We chose this building to try to demonstrate how to do this and whether it could be done, primarily because it was a concrete tilt-up building. And we're in the heart of Silicon Valley, and through the 80s, 90s, and even 2000s, this was the construction methodology of choice. There are literally tens of millions of square feet of this product type in Silicon Valley. We didn't really know this first building. ASHRAE named this the most innovative, sustainable building in the country. And we didn't really know if what we were doing was going to work, one, and we didn't know if it was going to be well received by the tenant community. My first tour was terrifying, and that ended up being the company that took the building. When we leased this building, the prospective occupant at the time walked through, and it was 48 buildings on their tour. And he said, this is the only one that was different. He said every other of the 48 buildings was the same building with different paint and color and a different carpet. And this was the only one that really differentiated itself from all of the rest. And so in a downturn, I think it's going to have much more resiliency to maintaining its occupancy and maintaining its value than a building that's built conventionally. So the way we get this building to zero net energy, kind of from a big picture perspective, is we use technology to maximize what nature gives us for free, and we try to have every method and building product serve multiple purposes. And we pretty much look to drive two things down. The two energy uses we're trying to reduce before we put a solar array on to generate what's needed is we try to reduce the amount of heating, ventilating, and air conditioning needed, and reduce the amount of artificial light that we need to produce. The way we reduce the HVAC loads is we insulate the building extremely well. Having a high performance envelope is probably the most important thing we did to the building. And we put 5 5/8 inches of insulation on the outside of the building, which keeps the inside, the concrete thermal mass available to be our air conditioner. And that gives us about an R20 insulatory value on the walls, and that's in combination with our electrochromic glass. And then on the ceiling, we sandwich all the thermal breaks from the solar panels and all that kind of thing. We sandwich it with 1.5 inches of foam on top, 10 inches of batt underneath, and that gives us about an R value of R40. And so that gives us a very high performance envelope to start with. And we ventilate naturally. Our windows are operable, our skylights are operable. They work with the building management system, which has sensors inside the building and sensors outside the building for temperature, air quality, wind direction, moisture content, those kinds of dynamics, to know when it's appropriate for windows to open, skylights to open, exchange the air. If the air quality outside is better than inside, we exchange the air when the conditions are appropriate. At night, we'll cool our concrete down to about 66 degrees. At the end of the day, it'll absorb human heat, computer heat. The air conditioner never needs to go on. It's a very efficient heat sink. And then at the end of the day, that concrete will have warmed up to about 70.5 degrees. So in the middle of the night, when the temperature has dropped, the building management system tells the windows to open, the skylights open, the fans go on, and we cool that concrete back down to about 66 degrees, and we also exchange the air at a time when it's the cleanest outside. So when the occupants come in the day, the thermal mass is ready to absorb heat again, and the air quality is actually better inside the building than outside, because we've got 3, 4 in the morning air inside the building and commute air outside the building. So that helps to drive down the need for artificial ventilation, for air exchange, as well as for heating and cooling. Our air conditioner and our heaters are almost never go on. So that drives that part of the energy need down. For the artificial light piece, we really didn't find anything on the market that worked well for what we wanted to daylight naturally. So the way we drive down the need for artificial light is we developed a skylight where the angle, the orientation, the aperture is exactly designed to see where those vectors of efficacy cross for maximizing, harvesting the maximum amount of daylight possible 365 days a year while minimizing thermal gain. And so we get an average of 19-foot candles of light on a 30-inch work surface, 365 days a year naturally, from an hour after sunrise to an hour before sunset. So that dramatically reduces the energy need for artificial lighting. So that, in combination with the reduced need for HVAC and air exchange, really drops that energy use intensity down significantly. This building, before we got involved with the renovation, had an EUI, or an energy use intensity, of 93. It's a British thermal unit, but it's a 93, and we drove that down to 21.5, which effectively means that we need now to generate about 25% of the energy to operate this building that we would have needed had we not done these improvements. So what that does is reduces the need for solar and power generation to about 25% of what it was going to be, and that reduces our first cost on the solar to 25%. The methodologies that we use to drive our HVAC needs down drove our HVAC equipment need from 100 tons on the building, which was here when we got here, down to 22 tons of equipment. So again, first cost is 25% or 20% in this case of what it was, less maintenance, less reserve requirements, and the economics all begin a domino effect that continue to accumulate. You know, one of the questions I get a lot is, what if everything breaks down? What if these methodologies don't work? Thermal mass isn't going to break down. There's nothing to break. We've got about 20% of the HVAC equipment that a normal building has, and it's almost never on. This building's been occupied for about 3 years at 8.5 people per 1,000 square feet, and I think the air conditioner's gone on less than 5 times. Everything we tried to do with this building, we tried to do thoughtfully. The landscaping is drought tolerant, native, needs very, very little water, very, very little maintenance, no grass, no cutting, no mowing and blowing. Everything we did was trying to use natural materials, repurposed materials, and do it in a way that lowered our maintenance. Everything was about lowering costs, lowering the maintenance costs of the landscaping. The exterior skin on this building is an elastomeric coating that's ceramic based that has the color embedded in that elastomeric coating, so we never have to paint this building again. Reduce maintenance costs. Because all of this was revolving around an economic model to try to demonstrate that this could be done more profitably than the less expensive way of building to code. In hindsight, now that the building's been occupied, it's extremely profitable. For every dollar that we spent over and above what we would have spent just meeting minimum code, we got $3 of value back. Yeah, I think a general takeaway to me for a building like this, if you're making the decision as to whether to renovate your building to meet minimum code in the traditional manner versus trying to do a renovation of this nature where it's net zero energy with the health and wellness aspects associated with it, what we have found is, as I mentioned before, we get about $3 back for every dollar we invest in the sustainability measures. So it's more profitable for the ownership. That's been demonstrated and proven. We have natural air, much higher indoor air quality, much better acoustics, uncommon thermal comfort, connectivity with nature 24/7 for the occupants. So you've got a much healthier environment for the occupant. Healthier occupants, there's a lot of studies that demonstrate that that means more profitability for the company. So our tenant is more profitable, so my credit strength is more reliable than it used to be. The lender now has a more reliable building that if it ever comes back to them has lower operating costs and it's a less carrying cost for them. So every angle that I look at a building like this, whether it's from the ownership, from the tenant, from the lending community, from the occupants that are going to be in it, it's a better prospect. And so we really are having a difficult time understanding, if you can do it this way, why you would ever choose to do it any way differently.